My name is Arabi Shammas. I am a senior lecturer at Cornell University. Sorry. So what is my topic today? I have a list of contents here. My presentation will start with the production of continuous basalt fibers, the production of basalt fiber BFRP rebar, mechanical and durability property of BFRP rebars. I will go through some of the design guidance, flexural behavior of BFRP reinforced concrete, comparison between the collected data and Eurocode design standards. I will go through a couple of projects and a case study. So what is basalt, continuous basalt fiber? So basalt is the most common rock type on Earth crust, and it's a dark in color, usually gray or black, and it's rich in iron and magnesium and silica. So the continuous basalt fiber is material made by melting the basalt rocks and extruding them into fine fibers. This process involves a single-step process. So the basalt is melted and then drawn back into fibers without any chemical additive. So this makes the continuous basalt fibers an environmental friendly and sustainable material. So the production of basalt fibers, basically the basalt fibers are produced from a natural basalt rocks, volcanic rocks. These basalt rocks are crushed and then melted into temperature about 1,500 degrees, then extruded through a small nozzle to form a continuous fiber. You can see that from the figure here. So, and then the fibers are winded to a roving. You can see it's like winded into a roving shape. This single step process doesn't require any chemical additive, making it eco-friendly. On the other hand, the glass fiber you can see on the left-hand side, right-hand side, the glass fiber are made from mixture of raw material like silica sand and other additive, which are also melted in the same temperature. The molten glass is extruded and cooled. The production of glass fibers also involve a multiple step with some chemical additives. On the other hand, the carbon fiber has a most complex production process with energy-consuming production method. Actually, this energy-intensive and multi-step process results in significant environmental impacts. Recently, today, I read that the energy consumption in producing or manufacturing carbon fiber is around 100 to 900 megajoule per 1 kilogram of fiber, while steel is around 20 to 30 megajoule per kilogram. Now, the basalt of RB rebar production. So you can see a figure is a production of RB is basically based on a Petrogen technology. Firstly, the continuous fiber, basalt fiber come from the roving grid will be collected into a feeding system. The fiber will be saturated fully in a bath of polymer resin. The process ensures that the fiber are thoroughly coated with the resin to enhance the bonding and mechanical property of the fiber. Now, the emerged fibers are inserted into a pultrusion machine. The fibers are pulled through a die that shape them into a desired bar diameter and bar profile. The bar will go through a curing tunnel, which causing actually to the resin to harden and bond the fiber together. Finally, the bar or the rebar is pulled out and then cooled to cut into a desired shape or desired length we need. I'll go through a bit for mechanical property of BFRP rebars. You can see that the mechanical property of BFRP differ from the carbon steel. The BFRP doesn't have any yielding points, and the behavior is a linear elastic, up to failure by about 920 to 1,650 megapascal. The elastic modulus of BFRP around third of the elastic modulus of steel. That means that we're going to expect higher cracks and higher deflection of the BFRP reinforced concrete member than for the steel reinforced concrete member. For the durability, which is the most important aspect for the FRP, in particular BFRP, where the BFRP is exposed to a different environment. For the left-hand side, the figures show the degradation of the BFRP with different exposure environment at a different temperature, while the right figure shows the strength retention for different environment and different duration. So you can see different environment are the water, salt, acid, and alkaline solutions are usually used to simulate high humidity, seawater, and de-icing salt, and acid rain, as well as the poor solution of concrete, respectively. You can see from this figure, left and right, particularly in the left-hand side figure, that the degradation ratio increased rapidly when the temperature exceeds 60 degrees temperature. It is suggested that the experimental temperature shouldn't go beyond 60 degrees because the uncontrolled degradation mechanism will be induced by high temperature. And also the research, durability research suggested that not all types of epoxy can work with the basalt. Resin can work with the basalt. So the recommended resin for the basalt is an epoxy, which has excellent durability. Also, the BFRP bar degraded fastest in the alkaline solution, and followed by water environment, the acid solution, and the lowest degradation, lowest in the salt solution. The degradation will be made worse actually with increasing the time, especially with the coupling action of temperature and high concentration solution. It's worth to mention that there's no clear relationship or correlation between the simulated environment and the service life structures. But some research suggested that 50 years of service life correspond to about 90 days of duration of exposure. For international design guidance, for the design of FRB in general, including BFRB, there are two steps. The first step is the physical, mechanical durability and the long-term performance of the BFRB should be expected. It should be obtained experimentally, and they should be accepted within the acceptance criteria of selected design code. These mechanical property, including the strength, the elastic modulus, the stress rupture, and the strength retention under aggressive environment. The second step indeed involved the design guidance proposed by selected design codes, which use the information from the first step we said. So the designer will take the information from the testing data and they design accordingly. Now, this is the idea for the whole design guidance, and there are a number of international design standards for FRB in general. ACI, which is the American standard, and the GOES, which is the Russian standard, cover all types of FRB, including BFRB. Now, for the next generation of Eurocode, FRB reinforcement design provision is given in Annex R of Eurocode, which is BSEN 1992. However, it doesn't include anything about BFRB. Now, the FIB number 40/2007 FRB reinforcement in reinforced concrete structures. There is a technical report, and that FIB report focuses on the use of FRB bars as internal reinforcement for concrete structures, highlighting their physical, mechanical, and durability properties. It also provides basic mechanical models and design guidance for ultimate and serviceability limit states. Now, there's an ISO standard, which is ISO 104.061/2015, and will be updated soon. And it specifies a test method for FRB reinforcement of concrete, focusing on FRB bar and grades. Now, more recently, I think this is one interesting one, which is proposed, which is a technical document, scientific and technical document by AFGC, which is a French. And it's provides recommendation for use of FRB rebar for reinforced concrete structure, which is a recent one. Now, a bit talking about the FRB reinforcement and about structural behavior. So I would like to explore the behavior of BFRB reinforced concrete member in comparison with the steel reinforced concrete members. We casted a few BFRB reinforced concrete beam, and the beam were reinforced with 2 rebars of 10 millimeter diameter. They were reinforced either by BFRB or steel rebar. So both BFRB which is basalt fiber reinforced polymer, BFRP, and steel reinforced concrete beam has the same reinforcement ratio. You can see from the diagram below, there's a comparison on the structural behavior between basalt fiber reinforced polymer, BFRP, reinforced concrete beams, and steel reinforced concrete beams. You can see from the left-hand side the midspan versus load, and you can see that the bending stiffness of BFRP reinforced concrete beam is lower than that for the steel reinforced concrete beams. And this is because if you look at the right-hand side now, that is because the stress strain behavior of BFRP is different, where the elastic modulus of BFRP is lower than for steel. Also, the bonding behavior, if you can see the bond slip curve versus bonding stress, the bonding behavior of BFRP differ from that for the steel. Mainly the bonding of BFRP is characterized by the chemical bonding with the concrete, while the steel, the bonding is defined and characterized by the chemical and mechanical bonding with the concrete. And you can see also from the load deflection relationship that there's no post-yielding deformation, which means that the reinforced concrete beam fell suddenly once the ultimate capacity reached. Now you see here the crack pattern, and you saw that figure showed the crack pattern and the failure mode, and it is clear that basalt fiber reinforced polymer reinforced concrete beam has more and wider cracks, as we explained before, that because the cracks, because there are the differences between the mechanical and bonding property between the steel and the BFRP. And it is higher, the crack width is higher than that for the steel reinforced concrete beam. Now, the steel reinforced concrete beam yield by steel yielding as we designed, while the basalt fiber reinforced concrete beam fell by either concrete crushing or rebar rupture, which is dependent on the reinforcement ratio. Here it's in a slide. There's a we started to work on collecting some data from the literature. Because there's currently no European standard that offers suggestion about FRP in general, including glass and carbon and basalt FRP. So with this project, we intend to use a large number of available test data, around 330 data points we collect in literature, to predict the ultimate capacity and load deflection behavior. With the use of proposed balance reinforcement ratio, you can see here the balance reinforcement ratio. We have two types of failure mode as we expected experimentally. The concrete crushing, if the reinforcement ratio of the BFRP is higher than for the balance reinforcement ratio, so the concrete will be crushing. And if the reinforcement ratio is lower than the balance ratio, the failure will be BFRP rebar rupture. We compare the calculated moment capacity, which is basically derived from the structural mechanics of the reinforced concrete with experimental data. You can see it's going to be it's showing a very good correlation. Similarly, we compare the shear capacity with and without using stirrups with experimental data. We assume that the FRP stirrups contribution is such that the stress in the stirrup reach about 0.45% times the elastic modulus, which means the elastic modulus, the strain in the stirrups is around 0.45%. And you can see it's not very good correlation with this equation. So we have to conduct some kind of reliability analysis. So by using reliability analysis based on Annex D of Eurocode 1, we propose a partial factor for flexural and shear design. And you can see the flexural was around 1.45, while the shear we propose it by 1.65 by using the Annex D procedure. But it's worth pointing out that the partial factor doesn't take into consideration the type of failure. So if we divided the data into two groups based on the failure mode of the reinforced concrete beams, we may have less conservative partial factor for flexural design. Now, here I would like to discuss about a recent project we conducted recently. So, which is a sustainable, durable, reinforced concrete structure using basalt fiber reinforced polymer. So we find in the recent year there are a number of companies and engineering firms has started specifying basalt fiber reinforced polymers in their design practices. This tends highlight the increasing recognition of the BFRP benefits and the growing acceptance in the industry. For example, as we said here, there's a client approached us to test basalt fiber reinforced polymer rebars and dowels. You can see here we tested dowels, we tested slab, we tested also the durability of the dowels itself, which is used for the dowels is used for the ground bearing slabs. And the objective, that testing was funded by Innovate UK, and the objectives of that project was were to reliable aggressive environment exposure testing data to obtain this data for dowels in acid and alkaline solution. Also testing the BFRP reinforced concrete to identify the cracks, and there was a different percentage added of the plastic fibers. Also testing a BFRP dowel solution to identify the capacity and deflection. So all this tested, and the company actually proposed design specification in line with the national design standard. Now, so this slide shows the result of the testing and durability behavior of basalt fiber reinforced polymer dowels. It's just a selective of some of the slides, and when they are exposed into alkaline and acid environments. They've been tested in 7, 14, and 90 days in alkaline solution and acid solutions. We only presented flexural and direct shear, but indeed the flexural direct shear also short beam testing. We didn't present these, but these data obtained from these tests are crucial for understanding how BFRP material perform in a harsh environment, and how can be directly applied to develop design specification for construction project. Now, for some of the successful case study, which is recently being conducted, which is by Smart Raft, which is Smart Raft by Arbus. So because of the testing being carried out, so as a successful story, the client was able to achieve a sufficient data to develop Eurocode compliant design approach to design Smart Raft for Arbus. Now you can see the company actually they specify the end product. So the end product basically an offsite prefabricated modular concrete foundation for barrier installation. And here is showing the step that being conducted. The first, you see the steel and BFRP cages, and where the steel were replaced by BFRP in the long beam. And it is a hybrid system. It worked very well, and I find the major benefit by using BFRP. Basically, there's going to be a reduced labor cost because the BFRP is lighter, and there's an reduced embedded carbon for the smart rafter because the BFRP has lower embedded carbon. So in conclusion, the basalt fiber is developed from volcanic rocks in a less energy intensive method, make it greener substitute. There's no need to add new components into the production process of BFRP, and there are no emission or hazardous substances. And to produce a fiber, there's a single stage of production, which is make it easy to produce, not like glass or CFRP. The elastic modulus of BFRP is lower than for a steel bar, hence, therefore, there's going to be a casual cracking deflation expected. Basalt fiber reinforced polymer dowels, now it's commonly started to be in the market, and it is very good for replacing steel and stainless steel dowels in ground applications. Now, I propose here some of initial research on after we collected data on regarding to the partial safety factor for shear and flexure design. Here we proposed. Thank you very much.
I'll be presenting on the performance of Basalt FRP and its embodied carbon savings what we have by using Basalt FRP as the internal reinforcement. So I've divided this presentation into 4 parts. Firstly, an introduction on why the requirement of this research, followed by existing literature review, and then the performance enhancement of serviceability of BFRP reinforced beam, very similar to what Rabi has done, but in terms of SLS, ULS, embodied carbon emissions, and cost. And finally, based on all the results what we have obtained, we'll come to some conclusions. The whole intention of performing this research is to address the climatic emergency in reducing the carbon emissions and limit the temperature rise to less than 2 degrees according to the Paris Agreement. The construction industry as a whole, which includes building and construction industry as well, contributes a total of 39% of total carbon dioxide emissions, according to a report in 2018. This just does not include just the part which is used in the construction. It also includes the manufacturing, transportation, recycling, and end of life as well. So we as civil engineers, it's crucial to work towards limiting these values, and this is where this research desktop study has been carried out. One of the ways of addressing this is by using naturally occurring material as an internal reinforcement, and basalt fiber reinforced polymer is a natural occurring material, and the manufacturing process was presented by Rabi a couple of minutes ago. So it is a low carbon material. It has many advantages over other fiber reinforced polymers like carbon, aramid, and glass. As also Rabi mentioned, we don't have a lot of codes or standard codes available to design this process. But however, we have an advantage of basalt being very similar to glass in terms of performance and degradation. So the available standards, which is the Eurocode 2, fib40, ACI, and CSA codes, can be used to uh, design materials with reinforced concrete with basalt fiber reinforced polymer as internal reinforcement. So in order to compare how the performance is, I've taken a geometry and the material properties from an existing literature review. So I have the experimental results, and when I do the SLS and ULS comparison, I have a reference material which has been tested in the laboratory to compare against and say, okay, the performance is okay. This code, the prediction from this code is okay. So I've used this material experimental work from the literature review El Gabas et al., which was published in 2017, where my beam one has only steel reinforcement, both for the longitudinal as well as for the stirrups, whereas beam two is with BFRP reinforcement, both for the longitudinal as well as the transverse one. Whereas in beam three, the only difference between beam two and beam three is that in beam three, I have a higher reinforcement ratio. And now the whole reason of increasing this reinforcement ratio, I'll come to it in the coming slides, which will be too obvious. In this literature review, the concrete had a compressive strength of 44 megapascal. The BFRP had a tensile strength of 1,724 megapascal, which is a bit higher with respect to the standard recommendations. And the steel has a yield value of 450 megapascal, and the modulus of elasticity of steel is 200 gigapascal, whereas the modulus of elasticity of BFRP is 65 gigapascal, which is almost one-third the value of steel. As Rabi mentioned, we do have a few codes, which is the ACI 441R06, a FIB Bulletin 4014 CSA, and in the UK, we follow TR55, which is for strengthening. Recently, in May 2019, FIB Bulletin 90 was published, and September 2023, Eurocode 2, where Annex J and Annex R are also published, where you can use FRP for the strengthening or use FRP as an embedded internal reinforcement. They do not give the equations for basalt as internal reinforcement. They give it for glass, which we can use. So in terms of coming to the first SLS check, in terms of crack width, the limit according to the code is 0.3. I don't know why this has moved up, but for 0.3 millimeter crack width gap, the moment from the steel reinforced beam, we reach 31.4 kilonewton meter. Whereas in terms of FRP, the Euro code has increased its value to 0.4 millimeter, at which rate the second beam, which is the BFRP beam with equivalent reinforcement ratio as the steel, has 22.8 kilonewton meter, less with respect to the steel reinforced beam. So when we increase this reinforcement of BFRP at the limit of zero point 0.4, which is the increased limit for the FRP materials, then we're able to match the 31.4 kilonewton meter of steel reinforced beam. In terms of deflection, uh, on an average, the second reinforced beam is lower by 135%, whereas the higher reinforced beam is improves, but it's still not that great. We are still lower by 62%. And this goes back to the point of the modulus of elasticity, where the modulus of elasticity of the BFRP material is 1/3 that of steel reinforcement. Comparing the moment of resistance, uh, the steel reinforced beam has a moment capacity of 32.9 kilonewton meter, whereas in case of similar equivalent reinforced Basalt fiber reinforced beam, which is beam number 2, we have 27 kilonewton meter, whereas the increased reinforcement ratio of BFRP gives us 39 kilonewton meter. This is with the safety factors, whereas if we get rid of this safety factors and compare it with respect to the experimental value, the prediction of the code against the experimental value in terms of steel is 41.4 kilonewton meter and 38.75, which is very close. Whereas when we compare it in terms of Basalt fiber reinforced polymers, in terms of two reinforced beams, the analytical value gives us 41.2 kilonewton meter, and the experimental one gives 71 kilonewton meter. Similarly, in case of higher reinforced beam, it goes from 60 analytical value to 91 in the experimental value. And the reason for this is because of the influence factors which are used in the standard codes, especially in the Euro code, where the tensile strength given by the manufacturer is converted to the 100-year design life by the safety factor. And then on top of it, we have these influence factors for temperature, service life, and environmental attack. And these values, what I've used for this, are the values which are provided in the code for the glass fiber reinforced polymers. So if I remove the safety factors, then my value still increases. This is somewhere where we need to work on having more closer values, and this can only be achieved with more experimental testings. In terms of shear resistance, the capacity in the capacity calculation, we use the modular ratio, which is the reinforcement ratio of FRP over the steel reinforcement. So this again reduces my capacity by 1/3. And whereas in case of minimum reinforcement ratio, minimum shear reinforcement, this modular ratio is included in the square root. So even if I increase quite a lot of reinforcement, it's still a lot of reinforcement required to match the steel reinforcement. So overall, in the shear reinforcement, the contribution by the FRP material in general is not that great, because the fibers are aligned in the longitudinal direction and the shear always in the transverse direction. And because these are linear elastic materials, they when they crack, they do not promote the aggregate interlock, and and there's a abrupt failure, which we where there's a ductile nature of steel is absent in this one. There are a few experimental works and analytical work which has been carried out, and these are a few references for them. Coming to the important bit, which is the embodied carbon emissions. Uh, I've used the concrete value of 0.103 embodied carbon dioxide emission per kg for concrete. And for the recycled steel, I've taken it as 0.98 embodied carbon dioxide emissions per kg. And this is from the iStrut E reference document. And for the BFRP steel, I've also taken it from a reference material, which currently the manufacturer has reduced even further. This value has gone even down. Uh, so using these values, when I calculate the total embodied carbon emission for producing that steel beam, it's a total of 67.8 kgs, whereas a second beam uh, has 44.8 kgs, which is 23 kgs less, but it does not fulfill my capacity requirement of either moment of resistance or shear resistance or crack width or deflection. Whereas when I increase this reinforcement ratio with an additional reinforcement in the bottom, do I still have savings? Yes, I do. This beam has 45 kgs of embodied carbon dioxide emission, which is still close to 30% savings in embodied carbon dioxide. At the same time, it does fulfill the moment of resistance with respect to the steel reinforcement. However, it's close to deflection and crack width, but still not quite there. So if I do I have real savings if I want to fulfill that specific requirement, which would be, for example, crack width. So if I want to match my steel beam, do I have savings? If I go on increasing the reinforcement, matching that performance, do I have savings with respect to BFRP? Yes, I still do, which is 22.3 kgs if I want to match the crack width. Similarly, in case of moment of resistance as well. So these calculations, what's been carried out is with reference to a very small beam, as we have seen. This advantage is seems small with 30%, but when we use it in large constructions, the savings is significant. These calculations of embodied carbon dioxide emissions, what I've shown now, is with respect to recycled steel. Now, if I use the same with normal steel, which has an embodied carbon dioxide emissions of 1.2 per kg, then my savings for that beam with 3 reinforcement ratio jumps up to close to 40%. So if I'm able to reduce my emissions from concrete or use a lower strength concrete, then my contribution from the reinforcement percentage increases and my overall savings also goes higher. And similarly, vice versa, the other way around. If I increase the concrete strength, then the contribution from concrete is higher and the contribution of the BFRP material goes down. The next part of it is the cost of manufacturing, where I've taken an average cost of concrete per meter cube as 175 pounds and that of steel as 1,500 per meter cube. And the average 10 diameter BFRP bar is taken as 2.27, again from a manufacturer. So the cost of manufacturing a beam of my reference material costs around 65 pounds in total, considering all the elements, whereas the same for the BFRP with just 2 bars is 116, but that is not of our importance. Going to beam 3, which is with 3 reinforced beams, the cost of manufacturing is 123 pounds, which is almost close to twice that of steel reinforced beam. So because it's a new material, because the manufacturing, raw materials, everything starts from scratch, or it's at the initial stages. This is why the cost of manufacturing is really high, which is very similar to what happened when we go back 10, 15, 20 years ago, when carbon was starting its application in civil engineering, where the cost of manufacturing was really high, whereas today, when it comes to strengthening, it's quite comfortably competing with other conventional strengthening techniques. So so if we start using more of these materials with the advantages of embodied carbon emissions, what we have, it will be it, it it's easier and a step closer towards achieving our 2050 net zero goals. And this is one of the research works towards it. So overall, based on this desktop study, the conclusions what we have come to is BFRP is a promising material and it can be used to design reinforced concrete elements. Uh, Plenty of literature reviews are available on the performance of BFRP bars. The only disadvantage at this point of time is that the tensile strength of BFRP or FRP in general is quite significantly reduced due to the uncertainty or the safety factors which is being used. In the current case, the design value comes down to 16.3%. The embodied carbon is low in comparison with recycled steel, but it is in a very good range with respect to normal steel. Uh, if if not, at least in the current market, in comparison with the steel reinforced elements, at least in case of stainless steel applications, this is a very good alternative solution at this point. Again, the cost of manufacturing is currently high, but higher manufacturing, higher consumption, higher usage will not lead towards lower cost, more applications. A few references which I've used, and thank you very much for listening.
I will be the final talk of this evening on the topic of Basalt FRP reinforcement. I will try to add new information and try not to repeat what Rabi and Chandan have already covered. I will start with a little bit of background. So focusing on steel reinforcement, because BFRP is an alternative to steel. The impact of steel making is currently at the level of 7 to 9% of global emissions. It emits around 2.6 gigatons every year, which is a huge number. However, this is not only because the impact of steel making process is quite carbon intensive, it's also because we use quite a lot of steel. Just last year, we have manufactured around 1.9 thousand megatons of steel. While the steel industry is making efforts and can and is doing quite a lot of things to decarbonize the process and so on, we can also look at alternative materials to use them where appropriate. And one of those alternatives are, of course, fiber reinforced polymers, this group of materials where basalt belongs. I will start with sustainability, talk a little bit more about that. But I wanted to talk a little bit outside of just carbon, because sustainability is not only about carbon rates and emissions. First thing that we need to look at is how available is this material? Is it a constrained resource? Luckily for us, for basalt, we're not talking about global availability on Earth. So it's quite widely available volcanic rock, the most common abundant igneous rock on Earth's crust, but it's also commonly found on other planets of the solar system. So we don't really have concerns that we're going to run out of basalt rock, which is great. The next thing is the manufacturing process, which Rabi already mentioned. The manufacturing process is quite straightforward and uses a single precursor, which is the basalt rock, unlike other types of FRPs. But what's also important is that it is a very materially efficient process. It has nearly 100% material yield, whereas glass has around 90 to 94% yield, and carbon has even lower material yield of around 50%. Next, there's been a lot of talk already about the CO2 emissions, so I won't dwell on this too much. But starting with a comparison with steel, if we look at the industry best current in UK, steel 98% recycled with the most efficient process available on the market. According to the EPD value, BFRP is very similar in emissions if we compare 1 bar of BFRP with 1 bar of steel. However, that best in the market steel, of course, is not representative of the average UK market, let alone the average global market of steel. So if we compare to the average figure for steel taken from the ICE database, BFRP has around 76% lower carbon equivalent embodied carbon per bar. Now, in my opinion, BFRP, because of its corrosion resistance, should be compared to other corrosion-resistant bars, not just to steel. So the most commonly used one, of course, is stainless steel. As we can see here, based on EPD values, BFRP is around 96% lower in embodied carbon per meter of a bar than stainless steel, which means we have a massive opportunity there for achieving savings. As has been mentioned before, this is quite a new material. So the process of manufacturing BFRP, even though it has progressed iteratively a couple of times over the past few decades, it has not fully matured and there is still room for improvement. So if we delve a little bit into the manufacturing process for BFRP, we will find out that the most carbon intensive part of BFRP production is, of course, the continuous basalt fiber production, and more specifically, the burning of the natural gas in the production of the basalt fiber. That means that if we wanted to improve or lower the embodied carbon BFRP even more, we could look to use more renewable energy sources. The next thing that we can look at is how does epoxy content affect the carbon emissions in a BFRP bar? And what this chart on the left-hand side is trying to show is that the contribution of epoxy on the overall carbon impact of BFRP bars is disproportionate to its content. So BFRP bar typically contains much more fiber than resin. However, resin per unit of mass is more carbon intensive than the basalt fiber. So that means that if we want to improve the process, that means we need to optimize the content of basalt fiber. I don't want to say increase it or maximize it because there is a theoretical minimum content of resin in order for it to impregnate and bind all fibers properly. But also we can look to use less carbon intensive resins which are available on the market. In other words, there's still room for improvement of the impact of emissions of BFRP, and it's already quite low. Finally, if we talk about sustainability, we should talk about circularity, which stands upon several pillars, and some of them are recycling or reuse, the energy efficient or eco-efficient build or manufacturing process, as well as extending the lifespan of structures. So while BFRP as a material is not recyclable in the same way as steel is, basalt fiber is, but more importantly, BFRP is quite suitable to the concept of extending the lifespan of structures because of its corrosion-resistant properties. Now on to the more practical side of this presentation. And I will skip over the properties because, of course, the previous speakers have brilliantly covered this already. But I will say, because of its unique properties, it's suitable for very specific applications. First of all, because it's magnetically neutral, non-conductive, it's quite suitable for applications where you would normally use non-ferrous reinforcement, such as stainless steel. This could be something like an MRI room in a hospital or a research institute. If we remember a couple of slides before where we compared the embodied carbon of stainless steel versus BFRP, BFRP is around 96% lower than stainless steel, means we have quite a massive opportunity to deploy this material to reduce the embodied carbon emissions of these kind of structures. Next, of course, we have the resistance to corrosion, and specifically, this means that it's quite suitable for marine infrastructure. We have coastal environments with high salt contents and humidity, but also general infrastructure where we might have exposure to de-icing salts, which is an aggressive environment as well. And this is precisely the application that I will focus on now. What's shown here is our Langeroork modular bridge approach, and the product that we focused on is called the abutment shell. It is a registered design of ours, and the abutment shell is a precast element that serves as a permanent non-participating formwork. It looks like a hollow cube, essentially, that can be very quickly assembled on site, stacked, and then cages are dropped in the middle and concrete poured in the center to form the abutment. While this element might not contribute to the most carbon impact of an entire bridge, it's quite a useful element to start with because it is a low-risk application, so it means it's quite suitable for implementation of novel materials. So what we did is we took our shell design, which was done, of course, in concrete and steel reinforcement, and we redesigned it to basalt reinforcement. We used the ACI 441 R15, which is the guidance document at the time. And we estimated that we can achieve around 22% carbon savings for A1 to A3, or the manufacturing modules. We can then achieve further savings in the transportation. That, of course, depends on the distance of the site to the factory. But using one example, we calculated around 11% saving on this particular part. The A5, which is the construction, changing to basalt doesn't really have an impact in terms of precast assembly on site. But most importantly, what we still need to calculate or quantify is the overall whole life carbon savings, because the material is non-corrosive. It is expected that it will result in significant savings in maintenance cycles and prolonging the lifespan of the structure. Here you can see what the two cages look like. On the left side, we have the standard traditional steel cage, which weighs around 1 ton. And then on the right-hand side, we have our new BFRP cage, which weighs only 140 kilos. It's a significant weight reduction, and that's how we estimated those savings in the transportation. These units were, of course, produced, manufactured, and then taken to the BRE laboratories for structural testing, measuring deflections, deformations, cracking, and monitoring the load on them to verify their structural performance. The way that they were loading is with 4 pressurized airbags that were simulating the pressure of the fresh concrete on the inside walls of the shell, and the pressures were increased gradually to allow us to inspect the unit and record the results. I won't dwell on the results just in interest of time for now, but you can see here very quickly the comparison between the control shell with steel reinforcement and our alternative shell with BFRP reinforcement. As expected, the BFRP reinforced element behaved in a much more deformable way, with experiencing higher deflections and higher cracking. But what's quite important for us is that especially the cracking performance matched the predictions estimated through our design, as well as that the failure, which in this case, failure meant complete destruction of the element, occurred at 3 times of the design load. So far, we've established that we can achieve carbon savings using BFRP in certain applications, and that the structural performance of the element can be sufficiently, can be designed with sufficient confidence. But of course, if we want to deploy it on a project, there is many more considerations that we need to take into account. The technical guidance, both Rabi and Chandan talked about. Of course, BFRP is not included in the Euro codes, at the moment, even though the 2023 update contains the informative annex, which refers only to GFRP and carbon FRP reinforcement. However, there are other international design codes, American, Canadian, Japanese, and so on. But also the task group 5.1 of FIB is working on 3 new bulletins, one containing the work design examples for FRPs, another bulletin for FRP applied as internal reinforcement, as well as a new bulletin on pre-stressing with FRP. And I will say a few more words at the end about pre-stressing. The next thing, similarly to assessing the sustainability, well, assessing the suitability of a product for deployment has to take into account the scalability, or how much of this material is available around the world. Will I be able to deliver my project, or is this something that's just lab scale and when we can do some tests with it, but not really deployed? Starting with the UK, currently the manufacturing in the UK from a single manufacturer is around 400 tons per year, and there is an equivalent factory producing another 400 in the States. Somewhat larger manufacturing facilities exist in Turkey and then in the Emirates with 6,000 tons per year, and then even larger capacity in Asia in locations such as Uzbekistan, for example. If we add all of this up together, it will be maybe some 15,000 tons per year, which if we compare that back to the steel production, which was 1.9 thousand megatons per year, it sounds very, very small. However, this quantity is still sufficient to deliver not just a single project, but multiple projects. And what can also be said, because the manufacturing process of the bars is in reality quite simple, the scale of production can be increased quite quickly. The manufacturers can introduce more manufacturing lines very quickly, and they can also work in multiple shifts. All that is needed is to see the demand. So supply will follow if there is demand. Following on, what other thing is quite important, especially for a contractor, is lead-in time. How would this affect our program? Currently, because the straight bars and mesh production exists locally in the UK, the lead-in time is around 2 weeks, which doesn't have a significant impact on production. However, we have experienced quite significant delays with the delivery of bent shapes, such as stirrups and so on, which exceeded a month in certain cases. But we expect that the manufacturing of bent shapes will start in the UK as well, and then we will have a lead-in time of 2 weeks for both straight and bent bars. In terms of the cage construction, the tying options are almost the same as for steel. So bars can be tied with a standard steel wire, and they can be combined with steel reinforcement as well without issues. We can also use plastic clips like the ones that are shown on the bottom right-hand corner. And of course, we cannot weld the bars, unlike steel. That's the only real difference. In terms of handling, we heard that the material is quite light, and you can see me in the picture lifting a 50-meter coil of BFRP. But don't do what I'm doing, because not because it's heavy and I shouldn't be lifting it, it's quite light. The problem is I'm doing that with my bare hands. So one should always wear PPE when handling a rebar, but this is standard PPE, nothing excessively required for handling BFRP other than gloves, long sleeves, and goggles. In terms of shape codes, I noticed there was a question in the audience, so I could use the opportunity as well to answer right now. The BFRP cannot be bent on site. It has to be formed during the manufacturing process in the factory, and it comes delivered to site already pre-bent. There are certain limitations in terms of shape codes. Most of the standard shape codes are available, but some of them are not. There is a full list available to see which ones we can or cannot use, but this can be resolved through clever detailing. One important thing to note that the tolerances the manufacturer claim are the same as for steel. However, we did experience certain issues with the shape codes not quite complying to the standard tolerances for steel. In terms of cutting off the bars, if it's needed, this can be done quite easily using any kind of saw or blade, just not using shears because that might split the fibers. And finally, as promised, a little bit of food for thought for the future. We heard quite a lot about poor serviceability performance of BFRP reinforced elements. They tend to suffer from larger deflections and more intensive cracking than their equivalent area of steel reinforced counterparts. So a concept that we can use that's quite familiar to all of us engineers is to use pre-stressing. So if we look at the pictures on the right-hand side, on the top we have a BFRP reinforced non-pre-stressed beam. On the bottom we have a BFRP pre-stressed beam. They have the exact same amount of reinforcement in them. The only difference is one is pre-stressed, one is not. And as one would expect, even by eye, we can see that for the pre-stressed beam, the deflections are significantly reduced, and so is the cracking. If we analyze the results, we can also see that the load-bearing capacity can be increased by 70 to 80% at the SLS limit if we apply even mild pre-stressing of around 30 to 40% of the ultimate tensile capacity of the bar. Pre-stressing with BFRP is not deployed at the moment on site. It's not really readily deployable as of yet, but it is a very interesting approach which can help us to overcome one of the main drawbacks of BFRP and use the material more efficiently. In the end, I will leave you with this nice photo I took a week ago in Sicily. This is a basaltic gorge. And I will say that BFRP as a material is an interesting alternative to steel. It should not be seen as a full replacement for steel, but for certain applications, it may come with quite interesting improvement, both in performance, as in terms of structural performance, as well as in reduction of embodied carbon emissions. And with this, I will end.